Hello everyone, this is Abhishek Kasturi and here I am presenting my small project on a price predicting model of machine learning learned with the aid of a course offered by Skyfi Labs. So let's start. We begin this project by importing various libraries predefined in Python that we require for building this project. Here are some example: NumPy, Pandas, Matplotlib, sklearn matrices, model selection, pre-processing, display, IPython display, SkyPy, etc. So these are the libraries that we require for running this model successfully. We have loaded the Boston housing price dataset using the function load Boston and then saved it into a variable called Boston. Now the boston.descr, or short form for description, gives us a small description about the table or the dataset that we have loaded. The information it gives is such as see the number of rows here and then all the attributes and what those attributes mean, etc. Yes, then coming back to the program. Now we have to build a data frame and we do this with the help of pandas. Remember, we have imported pandas here as PD as an alias name. Yes, so we use that PD dot data frame, and that's a function. We use all the data that's there in the Boston housing data set. The column names are taken from the feature Boston.features names, and we have stored this data frame into we have named this data frame as features. Now data frame is basically a table with rows and attributes. Now we can call any of these attributes by using this syntax features age. Now for example, if I want to know get the values that are there in CHAS, I can simply type CHAS here, and here you go. Every values that there in the CHAS column is displayed here. Fine. Now there's another thing. Since this is a supervised machine learning project, we have got another table called target. So this is our target pricing. That means for every value that is entered here, we've got a target price. This is basically the prices of the houses taken from the data, which actually depends on all the factors given here. So we have another attribute named target, and we've called it and we've put it into a data frame here. Now going down, fine. Now what we have to do is concatenate this target column with the table that's here. So we call the concat function, predefined pandas concat function. Now what are its attributes? The features list includes all these elements, and then the target axis equal to 1 tells us that it has to be concatenated as a column and not as a row, and we've named it as df. So when we call df, we get this new table here, or rather the new data frame here. Okay, the next one is the data frame.describe function. The describe function gives us details such as the number of rows, the mean of each column, the standard deviation, minimum, maximum of each column, 25, 50, and 70 percentile. So if we call this df.describe function here and round all the elements to a decimal of 2, we get such a table. Look, the CRIM column, the count is 506 for all columns, its mean, standard deviation for each column corresponding to, and then the minimum, maximum, and 25, 50, and 75 percentiles. Okay, so now we have to find the correlation between the target and each of the attributes here. A correlation, there's two types of correlation: a positive correlation and a negative correlation. So a positive correlation is one in which, let's take examples x and y. A positive correlation between x and y tells us that whenever x increases or decreases, y also increases or decreases as per x, so they're directly proportional in another terms. A negative correlation, they're inversely proportional. Yeah, so we have to find the correlation between the target and each of the columns. There are different correlation methods such as Kendall, Spearman, etc. that you'll learn through the course. Here we are using the Pearson correlation, so the correlation between each attributes in the table, that's what we want from here. Okay, yeah, so from the attributes that are all the elements in the table here, right, attributes in the list of features and its correlation with the target attribute, and then we take its absolute value and then put it in a list called cors. Now we have to zip the list. Zipping means pairing the corresponding elements of two different lists together. Okay, so cors is a different list and features is a different list, so we are pairing those the corresponding elements, the first element of the cors list and the first element of the features list, yeah, and all those subsequently, and then we are putting it again into a list stored in L, displayed L. Now we have to sort this correlation in the reverse order, or rather the decreasing order. Fine. So that's what this function describes here, and then once we are done, we have to unzip it again. What we did earlier, zip it, and now we are unzipping it, so we get two different lists were there. We zipped it into a single list, and now after we have arranged it in the decreasing order, we are again unzipping it. Fine. Now yes, we have plotted a bar graph here with the correlation values of each attribute in the features list, and then with the target attribute, right? So highest correlation means the dependence of target attribute is highest here as shown by the LSTAT, and the dependence of target is least on CHAS. Okay, so we store the values of LSTAT in X and target values in Y. Now print five values of Y here. Okay, yeah, so min-max scalar is used for normalization. Look, we have Y values of a wide variety of range from 36.2, 24, 21, etc. So it's difficult to handle. What we do here is we normalize it to a particular value. Here you can see everything is normalized from a range 0 to 1. Yeah, that's it. So min-max scalar is a function that's used to normalize a function, or normalize the values. Okay, so we normalize the X and the Y values taken from here. Yeah, now defining the error function. The error function is it's called the mean square error, and it's here are the mathematics of it, which we'll learn throughout the course, which I'm not explaining here. So it's just an error function. Now what we are doing here is splitting the data. In machine learning, it's a practice to split the data we've got into training and testing data set. So here we have split the X values as X train, X test, Y train, Y test. Yeah, now the gradient descent function, these two functions, yeah, I'm not explaining again the mathematics part of it. The mathematics you will learn through the course. Fine, so here we have described the update function, the gradient descent function. Yes, the program requires us to guess the values of the slope of the linear regression graph, and the y-intercept of the graph. It's just an initial guess, so here we're guessing these values, the error threshold, running rate, iterations, etc. Are as given, and then when you feed it into the gradient descent function, you get some return values. You store those return values in some other variables. Fine. Now coming to the visualization part of the graph. Yes, we have plotted the testing data, the y-test and the x-test. Those are the testing data sets. We have plotted those, and along with that we have plotted the training data. The training data is represented by the red line, and the testing data is represented by the green dots. Of course, here's a slight problem with the animation here. The animation requires what do you call, a movie player called FFmpeg. My compiler unfortunately doesn't have that FFmpeg. You can see here it has only pillow and HTML, so I'll have to rectify that, but I'll do that later. Now coming to the scatter plot. Yes, this is the same as this. Yeah, now we have plotted the variation of error with each iteration. As you can see, the error goes on decreasing and decreasing, which each time based on this graph. Okay, so that's desirable. We want this error to reduce. That we have achieved. Now coming to the prediction part. We are plotting the linear regression graph with the it's of the form mx plus c, right? Straight lines are of the form mx plus c. We have the x-test multiplied by the slope added, and then added to it is the y-intercept, and then we get the y points on the graph. Mean square error, we call the function the mean square error function, and we feed in the values y-test and predictions. The period data frame here again, so we make another data frame with x-test, y-test and prediction values. We name those columns as given here and store it in a p variable. Yes, so this is our training model. The blue dots here show the testing data set, x-test and y-test. It's represented with the help of a scatter plot. Now the tested and the predictions, our predictions is shown here by the red line. Fine, so our red line coincides pretty much in a nice way with the scatter plot. That's what we desired. And then after running a couple of functions again, yeah, remember we we normalized the function here, normalized the x and y values here earlier, so to get back the values as per our requirement, the pricing values as in the target variable, we need to unzip it. So all the inverse transform, yeah. So these lines of code here transform the previously transformed values of x and y in a reverse order, and then the predicted values. These are the actual y values and these are our predicted values. We put that in a table, in a data frame. Yes, so you can see that our predicted value are not so far away from the actual values. So that's what we wanted to achieve. We wanted to predict the housing prices in the Boston city. We have achieved this through our data rather machine learning model. That's it. Thank you and have a nice day.